All right, number 7, the big one. Complete the following table. So all I'm asking you to do here is draw the Lewis structure of this formula right here. Name the type of geometry, name the shape, and then tell me yes or no if it's polar. Okay, so here we go. So Lewis structure for H2S. I hope you guys realize that sulfur is in the exact same group as oxygen, sorry. And so it has the same number of valence electrons, therefore it's going to have the exact same bonding type as oxygen, right? Sulfur and oxygen look the same right here in terms of their valence electrons. So just like water, this has a bent geometry. And because all these negative things are up here, okay, we have, decent electronegativity difference there. We have some partial negatives up there, partial positives down there. So this is polar. CCl4. Got my central carbon, always my favorite. I'm going to surround the carbon with my 4 chlorines and spend half the video trying to draw all the valence electrons. Okay. Now, we do have some, quite a few dipole moments here. But notice that they're all evenly distributed around carbon. Okay, we got some negative out here, but that's balanced by the negative over here. It's got some negative over here, balanced by the partial negative over here. So this is not polar. Now this shape, okay, we have Sp3 hybridization right here. This results in a tetrahedral shape. BF3. I'm going to have a lot of dots here. Valence electrons, valence electrons, valence electrons, valence electrons. There we go. All right. Now, boron doesn't have any more valence electrons to repel any of these bonding pairs to send them into some sort of 3-dimensional shape. So this actually stays trigonal planar. Trigonal referring to the 3 points here. You have 3 points created by each bond between boron and fluorine. Planar referring to the fact that it's in one plane. Yeah, it's just a 2-dimensional flat triangle right there. Again, looking at the distribution of these charges, is it evenly distributed? Okay, because you better believe that each of these bonds has a great deal of electronegativity difference. But notice that they're evenly distributed around the central atom, so this ends up being not polar. Now, H2O, you better look and see the similarity here between H2S and H2O and be drawn essentially the same thing. Same shape, bent. Again, we have this pretty big difference in electronegativity that is not balanced out on both sides. Notice that the difference in electronegativity works in this kind of like down to up plane that's not perfectly balanced off by something on the other side. This results in water being polar. PCl5, central phosphorus, 1, 2, 3, 4, 5 chlorines. Valence electrons, valence electrons. Doubling the length of video. That's why I invented fast forward. Okay, so we have a whole bunch of these dipole moments between each chlorine and the central phosphorus, but notice that they are evenly distributed around the phosphorus. So this is going to result in this not being polar. Okay. Now, but in 3 dimensions, this is going to create something that is called trigonal Bi Pyramidal. Okay, again, trigonal because the base of the pyramid is going to be three-sided. Okay, it's going to be a triangle. It's going to be a three-sided pyramid, but there's going to be two of them. Okay, bipyramidal. One's upside down, and then they're both attached at the base. Okay, but that's going to be not polar. Not polar. I'll move the sheet up for our last two. BeF2. So I got beryllium, only having two valence electrons, so it can only form two bonds to begin with. That also tells me that all of its valence electrons are involved in bonding. That means it's not going to have any lone pairs. So this is going to just be Sp hybridization. And we have Sp hybridization. We're looking at something that is linear. Now we have quite a dipole moment here. Pretty significant one. Okay, but notice that they're balanced by each other on opposite sides. Okay, it cancels out that dipole moment. So this is not polar. And lastly, big scary one, sulfur hexafluoride. Sulfur is the central atom, surrounded by, you guessed it, 6 fluorines, with the most valence electrons yet. Hopefully you guys can see those, because I'm not going back and doing them again. So, this is a central atom surrounded by 6 atoms. Okay? That is the information that you need, that you use to conclude that this is octahedral. Okay? It's an octahedral shape, and it is not polar. Okay? Now, don't forget, I want you to be actively referring to table 6-5 in your textbook to help you with these things, to see the patterns, to get used to recognizing, like, oh, this is water, it's bent. Oh, this has a lone pair of electrons. This doesn't have a lone pair of electrons, because that is going to tell you whether or not you are going to have your molecule stay linear, or, like in the example of water, if you are actually going to bend your molecule right here. Right? It's the presence of these lone pairs that causes this to happen.